Okay, this is an exotic integral that we're going to solve using contour integration. So we need the residue theorem, which states that the integral over a closed contour C of your complex valued function f of z equals 2 pi I times the sum of residues of the function enclosed by that contour. And we're going to introduce the box contour over here, not the usual semicircular contour that we're so familiar with, or you would be quite familiar with if you're just starting your journey with contour integration. And the reason for not introducing a semicircular one is that because you have a circular trig function and a couple of exponentials in the denominator, so you can try using a circular contour, but that would make things look extremely complicated and a bit cumbersome as well because of so many exponentials involved, right? Because of the parameterization in terms of the semicircular contour. So that's why I'm going to introduce a box contour that works pretty well here. So let's name our integral I. And before we actually construct our contour, let's perform an analysis of the poles of our function. So the corresponding complex function is f of z equal to the cosine of z divided by e to the z plus e to the negative z. So we're searching for the values of z for which we have singularities, that is e to the z plus e to the negative z equal to 0. And you can solve this equation quite easily as e to the z equal to the negative of e to the negative z, and then you can use the natural logarithm in the complex sense. Now, we know that the natural logarithm of some negative number x in the complex world equals the natural log of -1 plus the natural log of x, and the natural log of -1, -1 is just e to the I pi using Euler's identity, and this equals I times pi. So what you're going to have here is -1 times this function, which gives you I times pi plus the natural log of e to the negative z. And this is pretty workable because you have some stuff canceling out quite nicely, and you're left with z equaling to I pi minus z, which implies that z equals I pi by 2. So that's where one of our poles is, and the only pole we will be needing, of course. So let's now consider the complex plane, and this is the x-axis representing the real part, and the y-axis represents the imaginary part of the complex number. And we know that our pole is I times pi by 2, so that's pi by 2 on the imaginary axis. So let's just make our contour quite convenient by letting it have a height, let our box have a height of pi, and let it run from -r to +r on the real axis. So this is what your contour is going to look like, and of course it runs in the anti-clockwise sense as always. Now let me just zoom in to have a better, to give you a better view of our contour. So the integral over the closed contour C equals the sum of quite a few integrals. First up, we have this integral on the real line going from -r to +r. So the integral from negative to +r, plus an integral over the right edge of this box. So let's call this RE, right edge, plus an integral over the left edge of this box, and another integral, the top edge of the box, that runs from, as you can see, +r to -r. So +r to -r. And first up, we're going to evaluate the integral over the entire contour C by using the residue theorem. So the integral over C of the cosine of z divided by e to the z, terribly sorry about that, that's worse handwriting than usual. The cosine of z divided by e to the z plus e to the negative z dz equals 2 pi I times the sum. Now there's only it's a simple pole, so you only have to evaluate one residue, the residue of the function f of z at z equals I pi by 2. And because this is a simple pole, it's very easy to evaluate. You have 2 pi I times the limit as z approaches I pi by 2 of z minus I pi by 2 times the cosine of z divided by e to the z plus e to the negative z. Now there's a problem here because it doesn't look like you have anything canceling out, and that's obviously because the denominator is not expressed in terms of a factored out polynomial, a nice factored out polynomial. So yeah, that's a bummer in this case, but it's not exactly a problem because we can use some trickery from complex analysis here. And the story goes like this, that you're evaluating the limit as z approaches some complex number z naught of z minus z naught times some analytic function g of z. Now the cosine of z is an entire function, meaning that it's analytic on the entire complex plane, divided by another function of z called h. And the story about h is that h of z naught is a zero of the function, and the derivative at z naught exists. So that's the story about h. And the story checks out for our function here. We have a 0 at z naught, which in this case is I times pi by 2, and the derivative exists. So we have no problems whatsoever applying this line of thought here. And the trick is, remember, there is no harm in subtracting a 0 from the denominator. There is no mathematical harm whatsoever. But we remember that 0 also equaled h of z naught. And forgive me, this looks like 3, but this is a z. Much better. Slightly better only. Yeah, forgive my handwriting. Anyway, so we remembered we subtracted a 0, and the 0 was actually just h of z naught. And we can do something even better. We can transfer this as part of the denominator of our rational function. So we have z minus z naught down here. Now look at the structure you have constructed. If I just move this closer to that limit operator, then notice that as z approaches z naught, the numerator will approach g of z naught. And down here you have the derivative of h at z naught, which we know exists. So that means to evaluate this limit here, all we have to do is take the derivative of the denominator, which in this case is pretty simple. The derivative checks out to being e to the z plus, oh, sorry about that, negative sign minus e to the negative z. So that means, continuing where we left off, we have 2 pi I times the cosine of I pi by 2 divided by this evaluated at z equals I pi by 2. So you have e to the I pi by 2 minus e to the negative I pi by 2. Now e to the pi by 2 is I, and e to the negative I pi by 2 is negative I. So you have I minus negative I, which checks out to being 2 times I. And the 2i cancels out, and yeah, this was awesome. So the integral over the closed contour C equals pi times, now the cosine of I times z equals the hyperbolic cosine of z. So you can replace this by writing cosh pi by 2. And with this result that we just derived, we can replace the left-hand side by pi times cosh pi by 2. And now we have to evaluate the integrals along these 4 edges of the box. So let me just let me just copy our contour down there for better visibility. No, yeah, I think I'm gonna get everything. So copy and paste. Yeah, so mission accomplished. Anyway, so this is where our contour is, and let me just remove some of these unnecessary arrows and markings, and yeah, that looks about nice. So let's talk about this integral here first. It's the integral from -r to +r of the cosine of, now you're on the real axis, so you can replace z by x, e to the x plus e to the -x dx. And this is your target function in the, this is your target integral in the limit as r goes to infinity. Okay, so we're evaluating all these four integrals for the case where r approaches positive infinity. So this checks out, and let's call it I. And what about this integral here, the integral along the upper edge of the contour? Let's write this out as the integral from r to -r of the cosine. Now, how does z transform along this edge of the box? Well, notice that the vertices of the box in the located on the upper edge are in fact -r plus I times pi, right? Because the height of the box was pi. And over here, it's going to be r plus I times pi. So we see that any complex number z defined on this edge will have a constant imaginary part, constant magnitude of imaginary part, that's pi. And it's the x variable that's varying between -r to +r. So from +r to -r, that is. So we have the cosine of x plus I times pi. And using, if we take differentials, then we just have dx, correct? So dx divided by e to the, now e to the x plus I pi can be written as e to the x times e to the I pi. And e to the I pi is just a -1. So this is -e to the x. And what about e to the -x? Yeah, exactly the same. E to the x, negative sign, and this plus turns into a negative as well, -x. And now you can do some cancellations with the negative sign. So you can factor out this negative sign. Then you have a negative sign out here. Okay. And if you switch up the limits of integration, you're going to have another negative sign, which cancels out the first one. So you have the integral from -r to +r of this thing here. Let's call this I sub 1, and let's call this I sub 2. And I'm just going to put a pause here for these two integrals because you can expand the numerator quite easily. So you can, I'm going to do that later, but first I'm going to try treating the integrals along the right and left edges. So yeah, so far we have things that are workable for the lower and upper edges, but what about now the left and the right edges? So let's talk about the right edge first. So the right edge, how is the z variable been parametrized? So let's just zoom in to get a better view. And this is what I'm looking at. That looks horrible, absolutely horrible. I am very sorry for that. I am deeply sorry for that. Forgive me. I'm just going to highlight it in white. So this is that path we were talking about, correct? And we see here that any complex number z will have a real part being equal to r, correct? And it's the imaginary part that's varying from 0 all the way to pi. So in this case, the differential element gives you I times dy. Okay, cool. So let's just write this out. So the integral over the right edge, sorry about that, the right edge is the integral from 0 to pi of the cosine of r plus I times y divided by, you have, because of the differential element, you have an I outside, and dy divided by, now e to the r plus I y would be e to the r times e to the iy, which is easy to work with relatively. So e to the iy plus e to the negative r times e to the negative iy. Okay, so that's the integral along the right edge, and the integral along the left edge would be quite similar, except that it runs from pi to 0, and you have a negative r here. So let's try to extract some information about the right edge that can automatically apply to the left edge. So first up, notice that we can actually expand the numerator. So right, this is the cosine of r times the cosine of iy, which of course is the cosh of y, plus sorry about that, negative sign, minus sine of r times the sine of iy. Now sine of iz equals I times the sinh of z, where sinh is the inverse sine, is the hyperbolic sine function. So I'm just going to write this out as, place the I over here, and you have sinh y divided by all the stuff down here, of which I plan on doing something with this e to the r term shortly. So e to the r, and I'm going to factor it out, e to the iy plus e to the negative 2r e to the negative iy. So now we're going to use, first up, let's call this I sub 3. And we know that the integral over some contour of a complex value function f, if you take the absolute value of it, it's going to be less than or equal to the integral over the same contour of the absolute value of f. So we're just going to use this sort of triangle inequality for integrals, and that means if I take the absolute value sign, I should replace, if I just take the absolute value of whatever I'm integrating, I should replace the equality by a less than or equal to sign. And we can actually distribute this, and the absolute value of I is, the modulus of I is just 1. We're not supposed to call this the absolute value. Sorry, slip of tongue, happens to me often. Anyway, so the modulus can be distributed over the numerator and the denominator. There. Are you happy I didn't say upstairs and downstairs, despite instinct telling me otherwise? So upstairs you have this modulus, and downstairs e to the r is just a positive number, and you have the modulus of e to the iy plus e to the negative 2r e to the ir and dy, of course. Now, what's the modulus of the complex number you have up here? Well, that is in fact the square of the cosine of, wait a second, I'm missing something, the r. There was an r here, right? Yeah. Sorry about that, terribly sorry. So once again, the square of the cosine of r times the square of the cosh of y plus the square of the sine of r times the square of the sinh of y. So e to the r and the modulus of this complex number here. Okay, so let's perform some analysis here. So we know that the absolute, the modulus of I sub 3 is less than or equal to the integral on the right hand side. And in the limit as r goes to infinity, we can say something definitive about the behavior of the integral. And we're integrating from 0 to pi, of course, once again. Missed quite a lot of stuff here, so terribly sorry again. So anyway, the square of the cosine is a bounded function, and so is the square of the sine function. So we have no troubles with convergence over here. However, this exponential term is our friend. In the limit as r goes to infinity, this exponential term also goes to infinity, so its reciprocal will go to 0, and the entire integral collapses to 0, which is awesome, because this implies that I sub 3 equals 0. And because of the similarity between the left and the right edges, what you can do is, if you perform a transformation from the y world to the negative y world for the left edge, and you make use of the even nature of the cosine function, and you don't even have to perform the complete analysis on paper. It sorts out to exactly the same thing. So obviously the integrals on the left and right edges of the box both collapse to 0 in the limit as r goes to infinity. So that is awesome. And now I can use all of this information. So I remember on the left hand side we had pi times cosh pi by 2, and this equaled the integral negative r to positive r, right? But we're considering the case for the limiting case for r approaching positive r going to positive infinity. So we have the cosine of x dx divided by e to the x plus e to the negative x. And the other integral you had was the integral from negative to positive infinity of the cosine of, let me remember, where was I sub 1 here? And this is I sub 2. It was x plus I times pi divided by, yeah, the same thing. Negative to positive infinity in the limit as r goes to infinity, cosine of x plus I pi divided by e to the x plus e to the negative x dx. So you can combine these two integrals because you're integrating over the entire real line in both cases, and you have the same denominator, so the cosine of x plus this term here that you can expand. So you have the cosine of x times cosh pi plus, minus sine, minus sine x, I sine x sinh pi divided by e to the x plus e to the negative x, which is great. And what you can do now is you can separate the real and imaginary parts. So you have a real number here, that's pi times cosh pi by 2, cosine of x plus cosine of x times cosh pi, which is just a real number, e to the x plus e to the negative x dx, and minus sinh pi is just a constant real number. Integral from negative to positive infinity of the sine of x divided by e to the x plus e to the negative x dx. And comparing real and imaginary parts on both sides, this is 0. And over here, you can factor out this cosine of x, and you'll have 1 plus cosh pi factored outside the integration times the integral from 0 to infinity of the cosine of x dx e to the x plus e to the negative x dx, and pi times cosh pi by 2. Which is awesome, because this is the integral that you needed. So all of this implies that I equals pi times cosh pi by 2 divided by 1 plus cosh pi, which looks pretty cool in its own right, but we can make it better. In fact, we can, because you can expand this term here, the cosh pi term, as the hyperbolic cosine of 2 times pi by 2, and use like that double angle formula, for the one for hyperbolic functions anyway. So pi times cosh pi by 2 divided by 1 plus, here you get 2 times the square of the cosine of pi by 2 minus 1, and the ones cancel out, the positive and the negative ones, and then you have one cosh up here and another one up here. Then you have this looks pretty bad now that I've mashed everything into one step. So it does look pretty bad from a mathematical perspective, but thankfully it's valid. So yeah, pi by 2 times 1 over cosh pi by 2, which is, of course, the hyperbolic secant of pi by 2, and that is the answer to your integration problem, which is, once again, extremely cool. So thank you so much for watching. Be sure to like and subscribe. See you next time.